How about now? Okay, great. So thank you very much. It's really a pleasure to be at PLMW. I've been involved with this workshop ever since it originated in 2012, I believe, and it's been lovely to see it grow every year and get more attendees every year. So as Nobuka just said, this is going to be a technical talk, but before we get into the technical stuff, I wanted to give you a little bit of background about me, what drew me to this field, and how I ended up where I am today. So I'm currently a professor at UT, and I happen to lead a research group called Utopia, and if you're wondering what that stands for, it stands for UT Program Analysis with some filler letters thrown in because it sounded good. And I'm really, it's been a pleasure to work with an amazing group of students at UT. And generally speaking, within programming languages, my research area is program analysis and verification, and I'm going to talk about some program verification research. But in recent years, I've also gotten into program synthesis, where the goal is to automatically generate programs from some high-level specification, and I've been doing a lot of work in the field of program synthesis recently. And if you ask me how did I end up working in this area, well, it was really completely a coincidence. When I was an undergrad, let alone doing, knowing that I wanted to do research in programming languages, I didn't even know what I wanted to major in. So I ended up, changing majors from like math to chemical engineering to CS like 3 times. And I didn't even know that I wanted to major in computer science until the beginning of my junior year. And I ended up working on programming languages because when I was an undergrad at Stanford, I ended up taking this compiler/programming languages class that was taught by Alex Aiken, and I thought that was a really super interesting class, so I started doing research with Alex, and I liked it so much that I ended up staying in it ever since. And if you ask me, what is it about this area that I really like and that drew me to it? There are many things, but one of the things that I find very appealing and generally about programming languages research is that it's really a very nice combination of theory and practice. And what I mean by that is, we often get to tackle problems that are of practical relevance. So for instance, how do you make software more secure? How do you get rid of a class of security vulnerabilities? How do you improve programmer productivity? So all of these problems are, in some ways, very practical. But, we don't, as the programming languages community, we typically tend to let principal solutions, and generally, whatever techniques that we develop come with rather nice guarantees. For example, we prove theorems like soundness. We like to have things that come with completeness guarantees and so on. Okay, so that was a little bit of background about me and what drew me into it. So now let's get into the technical part of the talk. And this technical part of the talk is going to have 2 parts to it. So in the first part of the talk, I'm going to give some background on program verification. So this is going to be, if you've taken any class related to program verification, I imagine that you would have already seen this, but in case you have not, this is going to be kind of a refresher. And then in the second part of the talk, I'm going to tell you about some of my own recent work on using a technique known as abduction to improve certain aspects of program verification. Okay, so to start from a very high level, so basically when we talk about a program verifier, this is a tool that takes as input 2 inputs. So you're given the source code of a program, as well as some specification. And sometimes when people hear the word specification, they tend to they tend to think of it as something scary. But you can think of a specification as it can also be something lightweight. It could even be things like assertions in your program, or it could be things like your program shouldn't have memory safety errors, it shouldn't have null dereference exceptions and so on. But it could also be something more involved than that. It can come in a different variety of forms. So the way program verifiers work is, given the program and the specification, they kind of stare at its source code. They don't actually run the program. And at the end, they generate what's called a verification condition. So this is basically a formula, typically in first-order logic, that has the property that if this formula is valid, if the verification condition is valid, then that implies the program satisfies the specification. And then once we generate this verification condition, program verifiers feed it to an automated theorem prover. So for example, something like most popular these days is an SMT solver. And if the SMT solver says your verification condition is valid, we have a proof of correctness. But otherwise, we don't really know. It could be either because your program doesn't obey the specification, but it could also be because of some sort of imprecision. So traditionally, verification is used for proving correctness, but not necessarily for falsifying the property. So it's over-approximate, in other words. So it turns out that today there are a whole bunch of deductive verification tools that you can play with. For example, Daphne, Boogie, ESC Java, Y, so on and so forth. But it turns out that under the hood, the basis of all of these program verifiers is a very nice and simple program logic named after Tony Hoare, or Hoare logic. And in a nutshell, you can use this Hoare logic to derive so-called Hoare triples that look like this. So here, S is some part of the program. It could be a single statement, it could be the whole program, or it could be some fragment of the program. And here, P and Q are formulas. So P is what's called a precondition, and Q is what's called a postcondition. And the meaning of this triple is that if you execute S in a state where P holds, and if the execution of S terminates, then we're guaranteed that Q must hold afterwards. Okay, so note that we're not proving termination, we're just proving partial correctness. If S terminates, then Q holds. And the nice thing about Hoare logic is that it gives a sound and relatively complete proof system for deriving all valid Hoare triples. And here, to be clear, when I say sound, it means that if you can derive a Hoare triple, then we know it's correct. And relatively complete, meaning that basically, if there is a way of deriving a Hoare triple, and if you have a perfect oracle for automated theorem proving, then you will be able to prove it. So all of this looks familiar to everyone? No, okay. Hopefully it looks familiar to some of you, but I won't go into the details of Hoare logic. Hopefully you've either already seen it in some class, or you will take a class where you will see it. But what I do want to emphasize for the purposes of this talk is, if I give you a program that doesn't have loops or recursion, then you can completely automate program verification. Okay, so, and the way you do it is, if you want to prove some Hoare triple like this, you go backwards. You start with your postcondition Q, and you compute something called a weakest precondition. And basically, this is a formula that encodes the weakest fact that you need to know in order to guarantee that Q holds afterwards. And then once you compute this weakest precondition, you just check whether your given precondition implies the weakest precondition you computed. And if it does, that means the Hoare triple is valid. Okay, so let's take a look at a quick example, because I don't want to lose those of you who haven't seen this before. So here we have a little program fragment, and here star just means non-deterministic choice. And here my precondition is y greater than 1, and I want to know whether after executing this code, whether x is greater than 0. So does this hold? What do you guys think? Okay, raise your hand if you say it holds. Raise your hand if you say it doesn't hold. Raise your hand if you're like, you don't know, which is also cool. Okay, So as many of you said, this is valid. So let's see why. So basically, we do a case analysis, right? So if we execute the then branch, we know x is 1, so it's positive. If we execute the else branch, x is assigned to y, but the precondition tells us y is positive, so therefore we know that x is greater than 0. So in order to automate the verification of this Hoare triple, as I said, what we're going to do is we compute a weakest precondition. And in order to do that, we're going to, again, do a case analysis. So we're going to compute the weakest precondition for the then branch. We're going to compute the weakest precondition for the else branch. And then, because we don't know which of those is going to execute, we need to ensure that both of them hold. So we're going to take the conjunction of those. So if we look at the then branch, what's the weakest thing that needs to hold over here to guarantee that x is greater than 0 afterwards? What do you guys think? Any thoughts? Nothing, right? It's just true, logically speaking. So in this branch, it's true. What about on the else branch? In order to guarantee x is greater than 0, what do I need to know before the statement? Yeah? Great. Y greater than 0, and if I take their conjunction, that means my weakest precondition is going to be y greater than 0. And in this case, I computed the weakest precondition. I'm just going to check whether the given precondition implies it, and it does, so therefore this program is correct. Now, what would happen if I change this assignment from x equals 1 to x equals z? What would be the weakest precondition now, and could I prove it? Could I prove it? No. Why not? What would be the weakest precondition? Yes?
Z is greater than 0, and you don't have anything about Z.
Z greater than 0, and y also greater than 0, right? And in this case, my given precondition doesn't say anything about Z, as you said, so therefore I wouldn't be able to prove this program. Okay? So the cool thing about this whole concept of weakest preconditions is if I give you a program with, just loop-free, recursion-free code, it's very nice, right? As most things are, if you don't have loops and recursion, you can completely automate reasoning, assuming you have a perfect theorem prover. Unfortunately, as you may expect, things get much more complicated when you have loops and recursion, and traditionally, program verification tools require human insight. They need a human to manually annotate the loop with annotations like loop invariants, method contracts, and so on. Okay, so, show of hands. Who's familiar with loop invariants? Okay. Just to very quickly review, basically, when we talk about a loop invariant is something that holds at the beginning of the loop before you execute it at all, and it continues to hold after every iteration. So it's an invariant. So now, what do we do with loops? So basically, whenever we see a loop, traditionally deductive verifiers say, well, I can't deal with them, they're too complicated, they'll ask a human to provide a loop invariant. So let's say we have a program that's annotated with a loop invariant. So just like before, we're going to check if my given precondition implies the weakest precondition. But in computing this weakest precondition, I'm going to use the provided loop invariant. So in other words, I'm going to say the weakest precondition for a loop is just the invariant provided by the human. But in addition to doing that, there are two other things I need to ensure. First, I need to ensure that whatever invariant was provided is actually strong enough to prove the property that I want to hold at the end. And second, I don't want to just take the user's word for it, because they might they're not perfect. They might have given me something bogus. So I want to, in addition, make sure that whatever information the user provided is actually correct. So how do we do that? How do we actually make sure that the provided loop invariants are correct? So the only way program verifiers, or the main way program verifiers know how to check whether your loop invariant is correct, is just by doing mathematical induction. So what do I mean by that? So remember, when you do mathematical induction, you have a base case and an inductive step. So for the base case, They basically just check whether it holds in the beginning. They check if the precondition implies the invariant. That's simple. Now for the inductive step, what we do, as always, is we assume the inductive hypothesis. So basically we say, assume that I holds before executing some arbitrary ith iteration of the loop. And then we ask, after you execute the loop body one more time, can I now prove that I continues to hold? Okay? So note that this boils down to proving this Hoare triple. Assume my inductive hypothesis. Assume C, which is the loop continuation condition. Assume the loop executes one more time. Then after I execute the loop body, can I prove that I is preserved? And note that if this doesn't have a nested loop, then we know exactly how to automate this. Okay? Now it turns out that if you have an invariant like this that can be proven using induction, that's actually a special class of invariants. Not all invariants are inductive, but all inductive loop invariants are, of course, loop invariants. So let's see what I mean by that. Okay, so let's take a look at this simple code snippet over here. So x and y initialize to 0, and then in each loop iteration, I increment x by 1 and y by x. And let's assume, to simplify things, we know that there are no, integer overflows. So assume we have mathematical integers. So here is y greater than or equal to 0 a loop invariant. What do you guys think? Raise your hand if you say it's a loop invariant. Okay, most people are raising their hands. Yeah, it is a loop invariance. It's not a trick question, right? It holds in the beginning. Y is initialized to 0. And then, basically, I increment y by x. And I know x is positive. So therefore, I know that y greater than or equal to 0 is a loop invariant. But is it inductive? Can I prove it using mathematical induction? Who says yes? Who says no? Who says I have no idea? Well, you must have one of those three, you guys. Huh? Okay. Let me give everyone like one more minute, and I want to see more hands going up. Okay, take a stare at this for a second. So the question is this y greater than or equal to 0? Can you prove it using mathematical induction, using the proof methodology that I just described previously? Who says yes? Who says no? Who says I still don't know? Come on, you need to raise your hand for one of them. Okay. So it turns out that it is a loop invariant, but it is not inductive. So let's see why. So the base case goes through, right? My precondition, what I know before the loop, y is initialized to 0, so I can prove that. But the issue is that my inductive hypothesis is not strong enough, right? So in particular, if I assume y greater than or equal to 0, I execute this code snippet, and I want to show that y greater than or equal to 0 continues to hold. But unfortunately, I can't, right? Because since my precondition over here doesn't tell me anything about x's being greater than or equal to 0 or about x being positive, I cannot show that y is incremented. It could, as far as I know, x could be minus 100, so in which case this code snippet would end up decrementing y by 100. So therefore, it's not inductive. Okay? So just like when you know something is true and you're trying to prove it using induction, but your inductive step doesn't go through, what do? Well, you strengthen your inductive hypothesis, right? So it's exactly the same when you're trying to do program verification. If you want to, if you have a loop invariant and your verifier keeps saying, no, I'm rejecting it, this I can't verify it, well, this is what you need to do. You need to strengthen it. And in this case, a strengthened loop invariant that is now inductive is y greater than or equal to 0 and x greater than or equal to 0, because this also holds in the beginning. And if you also know that x is greater than or equal to 0, you can show that both y and x are non-negative. Okay? Make sense? All right. Yes?
What's the definition of a loop invariant if it doesn't have to be inductive?
So the loop invariant, I can, it doesn't, I could, also define it with respect to execution traces, right? So this is one way of, this is how we prove that something is a loop invariant, by doing induction. But just because your induction doesn't go through, it doesn't mean that something, doesn't hold. It means it could be that your inductive hypothesis isn't strong enough. Okay? So basically, kind of to recap what we talked about so far, program verifiers are, really, really powerful, and they can completely automate verification if you have loop and recursion-free code. But, whenever you have things like loops, they require you to provide loop invariants, and not just any loop invariant. You'd better make sure that they're inductive, otherwise the verifier is going to reject it, and it's going to be very, very unhappy. And as you can see, even from our little simple example, coming up with these loop invariants can be non-trivial, and it can also be time-consuming. You have to constantly ask yourself, if I do induction, will my inductive step actually go through? So as you can imagine, there are a lot of different techniques that try to help users with that, and they try to automate, loop invariant inference or method contract inference. And, there are a whole bunch of techniques for doing that. And, I obviously, in the, during a 45-minute talk, I don't have time to explain you all of these different techniques. But I do want to kind of talk a little bit about my semi-recent work and tell you about how you can automatically infer these loop invariants using a logical reasoning technique called abduction. And don't worry, abduction in this context has nothing to do with kidnappings. It's actually a really cute concept, as you will see shortly. So in the context of logical reasoning, the best way to understand abduction is as the kind of the flip side of deduction. So to elaborate on that, when you do deduction, you have a bunch of premises, and you ask the question, what's a conclusion that follows from those premises? So when you do abduction, you completely flip this process. You're given a conclusion, and you also have a bunch of premises, but these premises don't imply the conclusion. So you ask yourself, what additional premises do I need so that the conclusion follows? So it's kind of like hypothesis generation. So if you want to formulate it a bit more formally, we can state it in the following way. So we're given a bunch of facts. Let's say we encode them as a logical formula gamma. And we have some desired outcome, some conclusion that we're trying to explain, let's say phi. So abduction is the process of finding a hypothesis such that, let's say this hypothesis psi, such that gamma and psi together entail phi. And in addition, we have a side condition. Remember, false implies anything. So we don't want to generate a hypothesis that contradicts what we already know. So in order to get to a state where we make our premise false, we're in addition going to require that our hypothesis does not contradict the known fact. So in other words, the conjunction of gamma and psi is logically satisfiable. Okay? So this is known as abduction, and as you can tell, this problem also doesn't have a unique solution in general. It can have many, many different solutions. And typically going by Occam's razor principle, you typically want to find a simplest hypothesis. You want to assume as little as possible when generating the solution to your abduction problem. So now before we continue, let's take a look at a simple example. So let's say I know the following premises. If it rains, then it's going to be wet and cloudy, and I also know that if it's wet, then it's slippery. Well, this is really simple. I can introduce a bunch of propositional variables, R to represent rain, W to represent wet, and so on, and I can encode these premises as this propositional formula here, right? Rain implies wet and cloudy, wet implies slippery. And let's say I wake up one morning and I observe that when I look outside, it's cloudy and slippery. So again, if I encode the conclusion in propositional logic, it says C and S. And As you can tell, my premises don't imply the conclusion, so now I ask myself, what am I missing from my knowledge base? What else would I need in order to observe this conclusion? So this is precisely an abduction problem, right? So basically you ask, what additional premise do I need to explain that it's cloudy and slippery? And any thoughts on what's a good hypothesis is here? The simplest hypothesis that you can think of that explains our conclusion. Yeah. It's raining, right? So if you assume R, then it implies definitely C, but it also implies W, and W implies S, so therefore that allows me to get to my conclusion. So therefore the most, the simplest solution to this abductive reasoning problem is that it must be raining. Okay, so now you guys are like, oh yeah, that's kind of cute. Yeah, I understand abduction is the opposite of deduction, but you're probably wondering, what in the world does this have anything to do with generating loop invariants and program verification? Am I right? Yeah, okay. So let's see how, this abductive reasoning idea helps us in program verification. And to see how it's helpful, let's again go back to our simple loops while some condition, do S. And let's say you have your precondition P, and we want to prove that Q holds afterwards. Okay, so, and we want to find a loop invariant that allows us to prove this. So basically, what we can do is we can set this up as an abductive reasoning problem. So in particular, we're looking for a loop invariant such that when the loop terminates, it's going to allow us to prove Q. So the loop terminates. When the loop terminates means the loop termination condition holds. So you have not C. And you're asking for a hypothesis that together with not C will imply Q. So if I can find a loop invariant that satisfies this condition, this is very useful because it actually, it's goal directed. It helps me to prove my conclusion. Okay? Okay, so that's good. I can use abduction to, generate a hypothesis, but remember, we're still just generating a hypothesis. This is something that needs to be tested and verified, right? So specifically after you do abduction, once you find a solution, there are three possibilities we need to think of. So one possibility is whatever loop invariant you generated can be proven using mathematical induction. So, you generated something and you give it to the verifier and it will be very happy. It will say, I can prove it using induction. Everything is great. Now, there's a second possibility, which is not as good as the first scenario, but still not too bad, is that whatever we conjectured is a loop invariant. We're kind of going in the right direction, but it's not yet inductive. We hypothesize something that's too weak, in which case we will need to strengthen it so that it can be proven to be correct. And of course, there's also the last possibility that our hypothesis is simply incorrect, in which case we're going to need to do something about it and recover from this hypothesis. So let's see how we're going to deal with all of these cases. So to get us started, let's say we're in the second case. We guess something that's an invariant, but it's not inductive. So remember, whenever you're in that situation, whenever you're trying to do mathematical induction and your proof doesn't go through, you strengthen your inductive hypothesis, right? So in this case, we're going to say, basically, I want to find a strengthening of my current invariant. My current invariant is I, and I want to find an auxiliary invariant I prime, such that if I prime also holds, then I can prove that I continues to hold. Yes?
Is it generally recognizable as an invariant if it's not inductive?
That's why we're trying to make it inductive. So for the second case, we don't know that we're in the second case. As far as we know, we found something, we can't prove it. So we don't, at this point, we don't know whether we hit the second or third case. Good question. Okay? But we're going to, yes. Yes. Okay? So in this case, we're going to optimistically assume we're in the second case, and we're going to say, find me some auxiliary invariant that allows me to show that I is an invariant. So in this case, the technical term for it is saying I is inductive relative to I prime. So how can I find such an I prime? Any ideas? Exactly, right? So we formulate this again as an abductive reasoning problem. So here we say, assuming the loop continues one more time, and I know that my invariant is correct, I want to find something that allows me to prove that I continues to hold, meaning that it entails the weakest precondition. And again, this is precisely an abductive reasoning problem, and I can ask my solver, and there are solvers for doing abduction. For instance, one that I wrote. And this allows you to find an auxiliary invariant, and using that, I'm going to strengthen my invariant to be I and I prime. Okay? And the idea here is basically you build this into a loop, and you keep repeating this process until your invariant either becomes inductive or you end up reaching a contradiction. So, for example, you end up strengthening in such a way that it contradicts a precondition that you have. So let me put this together a bit. So basically, this is how we're going to use abduction to infer loop invariance. So at every step in the process, we have our current invariants. And initially, these are just going to be true. We don't know anything about any loop. So then we're going to use our current invariants at every step to generate our verification conditions, right? So we're going to check, the weakest precondition is implied by the precondition. Everything is inductive, blah, blah, blah. Then we, just like always, we feed our verification condition to an SMT solver. If my theorem prover says they're valid, great, I'm done. But if it says it's not valid, unlike a traditional deductive verifier, I'm not going to give up. I'm not going to go back to the user and say, I can't do anything about it. Instead, I'm going to try to fix it and fix my annotations and try to do something about it by invoking my abduction engine. So in particular, I'm going to identify some clause of my verification condition that's not valid, and I'm going to see how can I fix this verification condition. And if the abduction engine comes back and says, there are no solutions, well, that means I contradicted something that I already know. So I'm going to combine this with backtracking search. I'm going to backtrack, and I'm going to go back to some previous decision level, and I'm going to try an alternative hypothesis. Remember, the abduction problem has many different solutions. So I'm going to backtrack and try a different solution. But then if the abduction problem does have a solution, just like we saw a few slides ago, I'm going to use that solution to strengthen my current invariant, and I'm going to end up with a stronger set of invariants. And I'm going to keep doing it, hopefully, until I'm in the smiley face case. But notice, in general, when we do program verification, we're obviously dealing with an undecidable problem if you throw in loops and recursion. So in general, this is not guaranteed to terminate. It may diverge. So in practice, you probably, if you use this method to infer loop invariance, you probably need to go to limit the depth of your search. So if you're wondering, well, how does this work in practice? Let's take a look at a concrete example. Okay, so here again, I have a little loop. So does this hold after the loop? Who says yes? Who says no? Okay, I think most of you need more time to stare at it. Well, it turns out that it holds, and let's see how we can prove that it holds. So if you use this algorithm, this technique that I just described, so we basically first say my current loop invariant is true. It doesn't imply it. So I'm going to say, well, use abduction to find me an invariant that will imply the post condition. And in this case, the simplest solution is to reassert the conclusion, and the abductive inference engine will come back to you and say, well, guess what? You need to know that I greater than or equal to 1 in the loop. So now in this case, we're going to check whether I greater than or equal to 1, whether it's inductive. And in this case, as we saw earlier in our earlier example, this is not inductive because it doesn't tell us anything about j, and we're incrementing I by j. So again, we set up another abductive reasoning problem. So we say, what additional information do I need to know in order to show that this implies my weakest precondition, or in other words, in order to show that I greater than or equal to 1 continues to hold at the end of after executing the loop body. And in this case, the abduction engine actually gives you a much more interesting answer, and it will tell you, well, you need to know that j must be greater than or equal to -1 before you execute the loop body. So now using this solution, we're going to obtain the stronger candidate invariant that I is greater than or equal to 1 and j is greater than or equal to -1. And at this point, this actually does become inductive, so your algorithm will terminate and say, yes, this program is correct, even though we didn't have any annotations or any loop invariants provided by the user. Okay, to summarize, so generally, program verifiers, to prove program correctness, they use deductive. Okay. They use deductive reasoning in the form of using a program logic like Hoare logic, and they also use deductive reasoning in the form of an automated theorem prover or SMT solver. But what I argued in the second part of the talk is that you can combine it with abductive reasoning to eliminate some of the burden that you require from the user. True, it's not going to work in all cases. We're dealing with an undecidable problem, but there are many cases where using this technique can, at least simplify the problem. And finally, I want to point out that, even though I told you about, an application of abductive reasoning just for inferring loop invariants, this technique turns out to have many applications. So, for example, you can use it for many parts of program verification, such as generating method contracts, generating method specifications. You can also use it in the context of program synthesis, it turns out. So, for example, you can use it to synthesize guards. You can, in our recent work at PLDI 18, we also used it to automatically generate correct by construction programs by figuring out places where you need to signal. And that's all I have, but if you have any additional questions, I'm happy to answer them.
Okay.
With abduction, do you ever have can you characterize is there ever a case where there's an interesting universal property you might want the formula that you're looking for to satisfy?
What do you mean universal property? Do you mean that your hypothesis may be universally quantified?
No, I mean could you ever have would it ever be interesting to have maybe you want to find the hypothesis which is, say, implied by anything else that would also work as a solution to the abduction or something like that?
So you're going back to this Occam's razor principle, right? In general, it has many solutions, but you typically try to find the simplest solutions. And what simplest means can vary depending on what setting you are, but generally speaking, you want to find the weakest thing. That's absolutely true.
Okay.
Yeah.
Oh, many questions.
So is the search of the thing in the question mark also, in some sense, analogous to the search of weakest precondition?
So if you don't have loops, then that's completely automatable. You don't need to do any guessing. You can do that using deduction. It's only when you have circular dependencies that abduction becomes useful.
So is this technique used in programming languages as Daphne, or if not, why not?
Sorry, could you repeat that?
Is this technique used in programming languages that permit program verifying? And if is not used in that programming languages, why not?
It's used in program verification literature. There are a lot of techniques that are based on abductive
Yeah,
reasoning.
but in Daphne, it is used in Daphne.
In Daphne, no, it's not used.
And
As far as I know.
it could be
It
implemented.
could be, but it hasn't been integrated. So this is like this work that I told you about, this algorithm, that's actually like a, like it's from 5 years back or something.
It may happen that while generating new clauses, the theorem prover may keep on generating clauses, but ultimately it never becomes an inductive proof. Is that possible? Like
You keep strengthening it, but it never becomes.
But it never
inductive.
actually
Yeah,
becomes
as I said,
inductive.
it can divert. So because we're dealing with an undecidable problem, so if you do this, you typically want to limit to how many clauses your guest candidate invariant has. Yeah.
Okay.
Wow, many questions.
Hi, I was just curious, what would be required to extend this to reason about programs with pointers? So is it as simple as encoding points to relationship in the invariants, or?
So in general, if you have a program with pointers, you can encode them as arrays. So if you have an abduction engine that can do abduction when you have the theory of arrays, yes, you could use that technique. Another alternative, which has also been done, if you want to reason about programs that manipulate pointers, you can use separation logic instead of for logic, and then you can use abductive reasoning and separation logic to do that as well.
Any questions?
So there's one on Slido. How is the reasoning about loops inductive? Loops may not terminate. Isn't it co-inductive?
Oh, so here, as I said, when you do program, like when you do horror logic, we're reasoning about partial correctness. We're not addressing termination at all. So termination is a whole different beast that I didn't go into in this talk. All right.
Okay. Thank you very much.
Thank you.